I think the stream is live. Yeah. Okay. All right. I think we should be good to go.
Cool.
Thanks, Anubhav.
I can.
Over to you.
I'll
Yeah.
start.
Yes,
Do you have
please.
any announcements or anything like that?
We'll do
Oh.
that. I think we've been waiting for 15 minutes, so we'll skip that and sort of jump to it and come
Okay.
back. I think
All
people
right.
are, yeah. All right.
Cool. Sounds good. Without wasting time, I'll start. I apologize for me being late. This is one of those weird days that I had to go through. I really apologize. I'm usually never late to speaking engagements. I'm also not in the time zone that I think probably most of people are. So I apologize for that too. So yeah, today we're going to be talking about service mesh beyond the hype. So the idea here is to kind of explore um, all things that kind of talk about the real story behind, like, what a mesh is about and what is this like hype behind it really. So a bit of a okay, there you go. A bit of a context about me. So I'm Mishra. I'm the technical advisor to the CTO. I work in the office of CTO right now at HashiCorp, but the the background, my background is very much in infrastructure and as an operations engineer. I did that and then worked on as a software engineer as well. So I kind of understand both sides of the story here to deliver software as software engineers and also operations. So I empathize with both sides of this I guess this software delivery world. Yeah, so so now I work as a technical advisor to the CTO. So I get to focus on kind of strategic company bets and projects, and working with Google and Amazon and Microsoft. And I get to kind of set the next 3 to 5 years for HashiCorp with the CTOs in the company. I'm Build 1.0 on Twitter, and just Anubhav Mishra on GitHub. So you can follow me there if you like. So as I said, like, I'm not in the same time zone as you all. So I live in this place called Vancouver in British Columbia in Canada. It's a nice place most of the time, but it's also known for its rains. It's also called Raincouver. In short, which basically it rains a lot. It rains a lot. It's not raining today, but it does rain a lot. I wish it was during the day. You could see like it usually is raining at this time. So yeah, it's also known for its rain. So I love open source. I worked on multiple open source projects. That includes a project that I created called Atlantis, which helps you collaborate on infrastructure using Terraform. And then I've worked on various Kubernetes kind of ecosystem projects like Virtual Kubelet. So I'm a provider maintainer for the Nomad provider. I've also recently done contributions to a project called Dapper, which was introduced by Microsoft. I think it's a project to kind of build distributed applications using some of the primitives that it provides. I also created and host the podcast called Hashika. So if you want to check it out, this is a shameless promotion. It's an infrastructure podcast that the Hashika produces, and yeah, it has like variety of folks, variety of guests from the open source kind of community. I'm also writing a book, almost finishing it. It's a book on HashiCorp Vault, a book on focused on security. So the idea is to kind of talk about how to get started with Vault and security for beginners. And yeah, you can check it out. That's the URL, vaultbook.com. All right, a bit of context on HashiCorp. So we make open source software. Our tools are better known than a company name, which is unfortunate. So this is like my regular marketing campaign about like, hey, there's a company behind these open source projects. So we build Vagrant, which is a developer environments tool, Packer, which is a server imaging tool, helps you kind of image on-prem and cloud instances. You have Terraform, which is more popular now. It's an infrastructure as code tool. We have HashiCorp Vault, which is a secrets management tool, kind of centralizes secrets management and gives you kind of somehow to contain your
Hey,
secret sprawl.
Anubhav, I think we're
We
seeing
have
only
no.
the title slide. Have you moved slides? Because we see only the title slide.
Oh, that's unfortunate. Yes, I have moved slides a lot. Give me 1 second. So I'll reshare. So I think this might have happened because I only shared one window, probably. Let me see. Okay, so you missed all my really nice slides. That's unfortunate. Like I had, okay. So I
All right.
talked about
Yeah.
this. I talked about HashiCorp. Okay, so we are here. So yeah, so I was talking about HashiCorp tool. So we make open source software, and we make six open source projects, actually eight now, with two new projects which we announced, I think this October. So I'll kind of quickly give you a rundown on HashiCorp software. So we make Vagrant, which is a development environments tool, Packer, which is a server imaging tool, Terraform, which is a infrastructure as code tool, Vault, which is a security tool, and then NAT, which is a general purpose cluster scheduler, Console, which we'll talk about today a little bit as an implementation detail of Service Mesh. And then new projects are Boundary and Waypoint. Boundary, it kind of gives you easy access to your applications using identity, which is a fairly new project we just released in October. And then Waypoint, I was actually personally involved in kind of the initial product work for Waypoint. It's a tool to kind of give you a build, deploy, and build, deploy workflow from like the first line of code to production. So that's kind of the rundown. So we now make 8 open source projects. It's a lot of open source stuff. So a bit about the company, HashiCorp, we focused on cloud infrastructure automation. We were founded in 2012. There's about 1,000 plus employees now. There's a bunch of funding, and we focus on the runtime, connection, security, and provisioning of applications. So these are the kind of the 4 verticals we focus on as a company. All right, so now to the kind of the actual subject matter that we want to talk about. So, okay, so before we get into anything, I want to kind of explore like, what is this hype, or why is the hype behind Mesh, right? So in the past couple of years, you might have seen if you were following open source, or you're following distributed systems, or you were following, things like schedulers and stuff like that, service mesh is talked about like a lot, and most people just, they know there's a thing called service mesh. When you ask them what it is, they'll have 18 different definitions of what it is, which is unfortunate, right? The origins of service mesh is actually in 2017 officially, and as the industry kind of coined the term service mesh. It was done by the creator of Linkerd, William Morgan. He wrote a blog post. I still remember this is in 2017, where they released the first version, I think, of Linkerd, which was written in Scala. And the idea was to kind of bring in some of the primitives that were learned in Twitter, and bring them and kind of wrap them in a proxy. And this proxy was a smart proxy that did like, health checking and, service routing and things like that. So that's kind of the origins of the mesh word. But service mesh, as in terms of the technology implementation, this has been done for many years, even though people don't realize that. But multiple companies have their own implementation of it, and it's still popular. And it's not a hype in real life, but because of this phenomena, there's this industry term that everyone talks about now. So when you do a search, what is a mesh? Like you'll see service mesh, you'll see like quite a lot of results there. It used to be half of it last year, because I did a similar talk last year, but I checked it today and it's ridiculous. It's gone up almost twice as much now. So it just tells you like how many companies and vendors are pursuing the space, even because it's hot at this point. So, and then you see tweets like this, right, from a bank in Europe, I think in Monzo. They say they have like 1,500 microservices in Monzo. Every line is enforced with a network rule that allows and denies traffic. And this is all done via, I think, a mesh. But you see that diagram, and I don't think that should make you feel comfortable or you should find it cool. I think that's quite scary. If you have a networking topology like that, it's cool that if you need that as a business need, it's great. But I think microservices also have like a lot to do with this mesh hype that you see today. All right, so before we get into any of the mesh and intelligent routing and things like that, I want to kind of follow along on the basics of like service networking. And people forget like, where does this all kind of begin, right? It really began with like a service wants to talk to another service. So in this case, service A wants to talk to service B, and in real life, like you can just like, actually have service A run on a VM, service B run on a VM. You can just point service A to service B via its IP and it's all good. But in reality, we all know that, service B really, like, there won't be multiple instances of service B. In reality, there's not going to be just one replica of a service running always statically, right? These are all dynamic in nature, especially with this scheduler world, right? Like you have You have Kubernetes and Nomad and Mesos and Docker Swarm. You can spin up containers and they go up and down all the time. And this, you might have multiple instances. So this is where a problem is introduced, and this problem is just a service discovery problem. How does service A discover service B? Whether it's in container or a VM doesn't matter. But how does this discovery process happen, right? So the second challenge is in real life, requests actually fail, right? You have situations where a request goes in and there's some network error, or the other backend might not be available. So do you retry? That's another interesting thing. Do you actually retry? Is that request an idempotent request? Like, these are the questions you want to ask when you think about retries. Then you have things like identity, like assigning proper identity to applications. So you might assign a certificate to service A, certificate to service B, and you can establish a mutual TLS connection, and that works, right? So there's this idea of establishing identity as well, right? Then you have things like, then you have things like authorizing, right? So, okay, service A can talk to service B, but should they be talking to each other? That's another question, right? Then, so this is all kind of all the challenges that you might face in talking about service networking. You have discovery, routing, identity, authorization, retries, circuit breaking, and also insights into your service, which is what we call another hype term, which is observability, just visualization of what's going on. That's another kind of challenge. So now let's talk about some of the first principles behind service networking, right? Like, what are the core principles that we think about? And when you talk about meshes, a lot of people just don't discuss this. This is just like already a kind of a given, and people don't even think like, why are we doing these type of things? But I think you should really think about what are the patterns that are available, right? So the first one is this idea of a dump pipe, and this has been around for a really long time, and we've done this a lot with multiple languages, with multiple frameworks. And one of the companies that's really like popular for doing this is Netflix, with the Eureka and Hystrix frameworks for Java and other languages. So here what happens is all the intelligent, for example, retries, discovery, all that is built into your application. So basically, your app has everything that it needs to talk to service B. So there's a library for doing retries, or maybe there's the same library to do discovery and circuit breaking and things like that. It's all built into your app. So when you build the app, you get the whole thing, and your network itself is super dumb. So that's why the name dumb pipe comes from. Is the network itself has no intelligence built in. It's just a network. You just want to make sure that service A should be able to talk to service B, allow like the security groups or the firewall rules, make sure that they're able to talk, and that's it. And that's kind of the job of the network. So there are some pros and cons to this approach. The pros is that it's very simple for the networks. There's a simplicity for the networks. The applications are smart, so basically what you see is what you get. So what you write in your application is what you compile and what's running. There's no other process. There's no other hop that you need to kind of care about. And all of this is like super customizable. You can actually change things as you like because it's all in application code. Super developer friendly, works really well. The cons here is that there is this redundant code. So you might have like multiple, libraries that need to be updated across multiple languages. So imagine you're a polyglot organization. So you're running Java alongside Golang, alongside Ruby, alongside PHP, alongside JavaScript. And you're building applications in all of those, and you want them to talk to each other. You might end up writing these libraries for every language. And then you have to update the life cycle of those libraries and everything. Because that's a challenge with this approach. So you now talk about what we call a smart network or a mesh, right? The service mesh. So here, what's interesting is all of those responsibilities that I talked about, like retries, discovery, identity, authorization, circuit breaking, all of that is pushed down to another process, which we call a proxy. It's just a process that's running alongside your application. This might be in a Kubernetes pod running as a sidecar container. This might be a VM just running as a systemd job. This might be a bare metal service, just basically just running alongside the application. It's responsible for doing all that. So service A itself doesn't talk to service B directly. It talks to its proxy, and the proxy forwards it to the appropriate proxy, and then the proxy that proxy basically talks to service B. So that's kind of the service to service loop, or like the life cycle of the request here. And some of the popular proxies that you know about is, of course, Envoy, Nginx, HA proxy, and we've been using multiple of these proxies for a long time now, right? Some of the pros of this approach is that there is basically little to no code, application code that's required, because all of these responsibilities are now part of this another process, right? So it's super nice. So you get like features like traffic shaping, service discovery, network policy control just out of the box, which is really nice, right? Like you can just have this other application, no matter what language you're writing your application in, doesn't matter. It should just use a consistent protocol like TCP or HTTP, and you're good to go. The cons here are that the smart network or the proxy becomes an implicit dependency of the application. So what that means is that the application developers are just focused on their applications, building the applications, making sure they're good. And if there's errors, they're like, oh, the bug doesn't look like in my application. Where is the bug? And then they have to trace through to figure out like what proxy out of, like, let's say in Monzo's case, there's a lot of these proxies probably running if they're using a mesh. Which one is the one that's throwing the error? Yeah, you can have like good smart observability to resolve that problem, but it still is a problem. Like it still is an implicit dependency of your application, and you may or may not have control over it, basically. So the holistic sense of the system, it's kind of quite a hard to reason, right? Like how does the system look like? Whereas in the dumb pipe case, right, there was no network hops. There's only applications that are talking to each other. You could kind of reason about the system, but in this case, it becomes really difficult to see a holistic view of the system. So now let's talk about the mesh, right? This is what we kind of talked about, which is the smart network, right? So we have service A, we have a proxy, we have service B, you have a proxy alongside it. So the portions of the mesh, what makes a mesh are these two things. So something needs to configure the proxy. So the proxy itself actually doesn't have much information. It needs to be configured by something, right? Like, for example, the service discovery data needs to come somewhere. What services should be authorized, that data is coming through something, right? And then there's the proxy itself, right? That's the second part of the mesh. So you have two things. You have a control plane, which is the part that kind of provides you with that config data and configures a proxy. And then you have the data plane, which is the proxy itself, which actually routes the packet. It's responsible for that. So overall, the control plane is responsible for things like, traffic shaping and routing and all of these rules that you have to store. So the storage mechanism is your control plane. It configures the data plane accordingly. It gives it service discovery data. It does policy enforcement. So basically an authorization call, for example, in our previous case, when two services had established a connection, are they allowed to talk to each other? To answer that question, the control plane needs to kind of tell you whether they are allowed or not. The control plane stores all the policies and the rules that are to be enforced by the proxy. So it is the kind of the brain of the system. It should be highly available. And this is the portion of the system that you want to be highly available. Some of the examples today, you have HashiCorp console, you have Istio, you have Linkerd. They all have control plane portions of the mesh as well. Then you have the data plane, which is basically the thing that's routing these packets, right? It's forwarding, requests to the application. It's doing some health checking. It's doing some form of load balancing, maybe circuit breaking timeouts. It's actually enforcing what the control plane has told it to do. And these proxies are, Envoy, Nginx, HA proxy, Fabio. There can be many. This is all pluggable interface, right? The idea is to kind of make it super pluggable so people can use what they like, which works for their organization. All right. So the second thing that I think, and another thing that I guess not too many vendors talk about, is this protocol awareness, right? Like no one really gives you this choice. They say like, oh yeah, you have HTTP services, you have gRPC services, you're good to use a service mesh. But no one really talks about like what it means to be protocol aware. So you have this concept of layer 4 versus layer 7 proxies or layer 7 meshes. So layer 4 is, you already know, TCP, UDP, right? Layer 7 is HTTP. So layer 4 is basically any mesh that allows you to gives you like layer 4 compatibility. It kind of makes it universally compatible because, everything is kind of built on top of like protocols like TCP, UDP, and things like that. So you are by default universally compatible. You get high performance because there is no inspection of the request happening here. It's just basically pure streaming connections that are going from one place to the other. So it's high performance for those type of meshes, right? And the last thing is, you don't actually, the one of the con is you don't actually get like sophisticated features like, you know, based on my cookie or based on my host header, route this request, because we do just not inspecting the request here, right? So that's kind of one of the trade-offs here. In layer 7, you can actually perform some complex routing decisions. So you can actually do things like, hey, based on my cookie, based on my host header, based on my path, route me somewhere, because you're inspecting the request. And as a consequence, it yields to lower performance. And most people actually don't see this lower performance because you're not hitting that scale. But believe me, when you hit a certain scale, you will care whether you want to be layer 7 or layer 4, based on like particular parameters that you see basically. So you can do things like header based routing and path based routing with HTTP with layer 7 protocol aware proxies or service meshes. All right. So one of the things I want to talk about is, of course, I talk about open source stuff and talk about an implementation of a mesh, and like I can kind of share the story of like how console works, and maybe this gives you a good example of like what a mesh can be. And it's really hard to just talk theory and not kind of imply. And maybe hopefully I don't know if the demos will work because they weren't working when I was like putting this talk together, because I was using some like really development build of things. Hopefully it all works out here. But quickly talk about console. So console has been around for a while now. So it was created in 2014. It's fully open source, free to use, free to download. The vanity metric here is the GitHub stars. You have about 20,000 GitHub stars on GitHub. We get about 1 million plus downloads, and this number is actually outdated. I pulled this out last year. This might be more than that, but we get about 1 million plus downloads. We do have customers that are running, 50,000 agents, console agents, in a single data center. So they have a really large deployment, and they do it successfully. Amazon actually recently told us last year at reInvent that console is like the most popularly, I guess, one of the most popular service mesh discovery tools on AWS. It's most widely deployed on AWS, and AWS, as you already know, is the leading cloud provider today. So some of the public users that use that say that they use console, we can. I wish I could share more, but these are the ones that we can kind of actually share. Others are like these large enterprises that they do not want to talk about what they use. So we have things, some of the logos you might recognize. You have Stripe, DigitalOcean, which is a cloud provider, Slack, Cloudflare, Target. We have folks like UBS, which is a bank, SAP Ariba, Capital One, Twitch, which is a streaming service, Citadel, which is a large hedge fund, eBay, and GitHub. They all use console, and anything you might do today with these tools actually probably uses console in the background here. So this is where, I'm going to skip a lot of stuff about console, but I'm going to just focus on the mesh stuff that relates to console. So I think in 2018, we released, I might be wrong, no, I think 2018, we released a new feature for console called Console Connect. So this is our service mesh feature that allows you to do service-to-service communication in a secure way. So we give you automatic TLS encryption on any service. And when I say automatic, it's like actually zero touch, and hopefully I can show you in a demo. And then you do things like identity-based authorization, so you can kind of create rules that allow you to deny certain services to talk to certain service and so on. And it does work everywhere. So the Console Connect actually is one of the uniqueness of this project, is that you can run it on-prem, you can run it with containers, on Kubernetes, on ECS, on Docker Swarm, on just native Docker, on Nomad, on bare metal, on VMs, anything you like, basically. So the problem basically here is that you go from one IP to the other. It means before, the way we were doing this, we had a firewall, we had two machines, and you just allow the firewall, you allow an IP address in, and it all just works. But we were doing this all over plain TCP. So anyone that's just basically dumping your network is able to listen in on the network, can actually see what you're sending, which is not good, which we want to kind of get away from. And if you're doing this in production today, I would really recommend looking into any one of the service meshes or anything that allows you to do some form of encryption, because it's not good. So in today's world, what has happened is you have multiple applications running on a machine, and they all have names, And you can still do this. You can still establish mutual TNS connections. But what if the DB instance actually moves from that IP address to another IP address? And so you can't really kind of uh, you can't really like establish real authorization via IPs in a world, especially that's dynamic in nature, which you have like multiple instances coming on and off, right? So that's where you kind of bring in this proxy idea, right? So what happens is, instead of API talking to DB directly via just plain TCP or something, you could establish a local connection to your proxy, which is intelligent enough to figure out, hey, how many DB instances are available? Okay, I'll route it to the most closest to me, or the one that's healthy, and it can forward the request to the appropriate proxy. The proxy can forward the request up to the database. And for the API itself, it actually just thought that that DB service was locally available to it, and it's just talking on a local host port, which is really, really, really nice. And there is a mutual TLS connection between proxy to proxy, which is usually persistent, and you have a low overhead. It's just given, like, if you establish one connection, once you establish trust, you should be able to kind of just pipe through request afterwards, and it gives you performance right there. Some of the layer 7 things you can do with console. So for example, you have a service called you're requesting for a web.service.console, and you're requesting like a certain path or something. You can do a lot of different things. So let's say I'll take you step by step of how you can kind of route the request with console. So let's say you want to do some form of HTTP routing. So you can do based on path, which is exact prefix regex matches. You can do header-based routing. You can do query-based routing. You can do HTTP methods-based routing, and there's multiple other ways of doing this. We constantly try to add more features here. This is where and developers kind of want to take this feature. So you have, let's say, in this case, we want to say is that, okay, service, a request coming in for service web, if it comes to the path prefix admin, then basically rewrite that path to just root. So just change /admin to /, and then it should actually go to a destination service called admin. So none of the definition here, and by the way, this is HCL, this is HashiCorp configuration language. It's made for kind of humans to read and write here. So the idea here is, if you see, none of this stuff actually says like what machine admin is running on, or what's the IP of admin, or anything like that. You're just using the logical name of the service, and that's all you need to do. And especially in the world of containers, this really helps. So that'll rewrite the path to /, and then maybe you can apply a traffic splitting rule where you can kind of create these subsets. So you create a subset called V2 and V1. So this might be version 1 of your application and version 2 of your application. And then you can maybe split the traffic. You can say that, hey, 10% of the traffic should go to our new version, and make sure that's all good. And then 90% should be just going to the V1, which is your old version here. So as soon as a request comes in for an admin, we match on this, like we basically look for this service splitter, and then we just split the request. In this case, we'll return, let's say we matched on version V2, we'll return you the healthy instance for V2, basically. And the subset itself needs to be defined. Here, if you see, the default subset here is V1. So most requests should go to V1, and then a subset of requests should go to V2, and then you can match based on like any metadata on the service. So in this case, I'm just using version, but you can kind of see where this goes. So you can actually, maybe define a metadata that says, I'm running in the compliant, infrastructure, or I'm like the PCI compliant hardware, or anything like that. And then you can do routing based on that. So special requests can actually enter into PCI compliant infrastructure versus just general infrastructure. So yeah, so that's kind of the idea of kind of resolution of the whole thing here. All right, so now this is all good, happy and dandy, like there's no issues, right? Like, but in real life, what happens is, for example, you have one service running in a certain address space, and the other service running in the other address space. Most meshes actually fail right here, because there's no way to extend them, especially when you have like unroutable IPs that are happening here. Especially in the case, I don't know if you've noticed, in the case of Kubernetes, you'll see all these like default clusters that are running in Google, Amazon, Azure, Microsoft Azure. And you'll see they have overlapping IP ranges. So there is no way for a service to run on run on one cluster and talk to the other without doing some form of like port mapping or like some form of natting basically. So to resolve this, we released a feature called mesh gateways. So this basically allows you to securely talk to networks that basically you don't really need to care about overlapping and non-overlapping thing. So what happens is that you, instead of like talking to the thing service directly, you just talk to your local mesh gateway, and then that mesh gateway is intelligent enough to talk to the right mesh gateway that has the service. So for example, service API wants to talk to service DB. The service API will actually just say, hey, I want service DB. I don't care where it is. Just give me service DB. And then if the local resolution doesn't work, so let's say the DB service is not running locally on that same data center, the request automatically gets forwarded to the mesh. You can define this. You can say, hey, like, do not forward my request to the mesh, or always forward my request to the mesh. So you can configure all of this. It's all configurable. But the mesh is intelligent enough to figure out, like, hey, where is the healthy mesh, the other mesh gateway that has the DB service, and then the request is just forwarded all the way through, and then the response comes all the way back, and the API service actually doesn't notice anything, which is really, really nice. So you can kind of connect, your on-prem stuff with EC2, with maybe some Kubernetes clusters that are running somewhere else, and this is all can be connected via these gateways. And these gateways are the only thing that you want to publicly expose. So you won't be exposing any of the other stuff like console servers, clients. You don't need to expose anything. You just expose the gateways and make sure they can talk to each other on a secure port like 443, and the rest is all taken. Okay, I'll show you this later, by the way. So the security portion here is that the gateways cannot decrypt any payload. So basically, if you have any, there's no keys on these gateways. Only the end service that can actually talk to you based on authorization has the private key already provisioned to talk to the service. And this all works using SNI headers. And by the way, this is not anything novel. Like, people have been doing this for a really long time. Console just gives you a very easy way of doing this, and it just works out of the box. And then you can also do intentions across data centers, which is cool. So basically, you can say, hey, service API should be able to talk to service DB, but service web shouldn't be able to talk to service DB. Now, since these intentions are global, and so console is multi-data center aware, so you might have two console data centers running. You can join them together. But when you create an intention, those are global. So basically what happens is, if web service tries to talk to DB, and let's say the DB is in some other data center, it wouldn't work. If it's in local data center, it wouldn't work. So it's kind of globally enforceable, which is really nice. So you can kind of see like your whole data center with a single view. And instead of like thinking about them in disjointed IP ranges and disjointed, environments like containers versus VMs, kind of just think about things in service primitives and as logical names of the service. Forget about IPs. You can just focus on building applications and not care about like all of this other thing. So this is what kind of is the real beauty of like using a mesh and really getting most out of it. Now, of course, you get all the other features like visualization. So you can actually see here, you get a network topology graph where it says, hey, data center one has a service called web. It can kind of output its metrics, and it's connected to maybe service API or some other service and so on. And you can kind of show some form of metrics, some basic metrics that give you an idea whether the service is doing okay or not. All right, so that's that. I wanted to show a quick demo. Now, again, this may or may not work. So this wasn't working before I started doing this, preparing this talk, because I'm using like I should have really used like what do you call that? Like a stable build, but I'm using a dev build of console. Console 1.9 just got released, so I wanted to try it out. And I'm very ambitious. So if this doesn't work, we'll abandon the demos and we can go to Q&As. But I'll try my best. Hopefully this just works, right? All right, so I hope you all can see this. Nishant, can you see the terminal window?
Yeah, I think like if you could increase the font size slightly, it would help.
Oh yeah, for sure. How's that?
Yeah, much better.
Okay, so I will have that here. And then we'll have, Okay, we'll have this here. All right. So here I have a Kubernetes cluster that's already running. Let me see. All right, here I have a Kubernetes cluster that's already running console. So I'll do kubectl. This is, I think, a 3-node cluster. So I'll do knode. And you'll see there's 3 nodes. So if I do kubectl get pods and grep for console, you'll see like there's a bunch of these things running. So this is what, when you install console with a Helm chart, this is what you get out of the box. So you get like the servers. I highly recommend that you should, you can run these servers because these servers run as a stateful set. But ideally, if you're running like something in production, I would recommend not to run the servers on Kubernetes. Just run them independently because you anyway don't need to run many. 3 servers are good enough for a really large number of nodes. But yeah, it means that's my recommendation. But it's very easy to do on Kubernetes too. There's no harm in it, but I think I recommend, as my own personal operations experience, I recommend just not running them in Kubernetes. But yeah, that's that. And these are the ones that are just the clients that are running on every node, basically. So these three are daemon sets that are just running on the on the nodes themselves, basically. So today we'll be kind of using 3 services. I'll make this bigger. So we have a service web, which you can kind of think about like as your web front end into your application. There's 2 of these instances, and we're going to do some interesting things here. And this is all using via annotations, and this makes it super easy to use a mesh, right? So here what I'm saying is I'm providing an annotation console.hashicorp.com, and I'm saying connect inject, basically inject a sidecar proxy for me. That's what I'm saying here. And I'm saying my service name is service web. If you don't provide this, we use the first container, I think. I'm explicitly providing this here. And then I'm saying something that I'm saying like my upstream is service API, and I want that available on 1991 locally. So here what happens is basically what I'm telling console is that, hey, like, I want to talk to service API, which is my upstream, but I don't care where it's running. Just give me that available locally to me on 1991. And then I'm just using an upstream here, URL, which is localhost 1991. So I'm able to just hit it locally. That's kind of the idea here. And then if I switch to the service API here, so it's another like really simple service. By the way, these services are very, very simple. All they do is, message back with a message. There's nothing crazy about this. The service API here, again, does the same thing. I'm just defining a Kubernetes deployment with 1 replica. And I'm saying, the service name is service API. Then I'm saying I want an upstream of service hello. So this is another service that I'm calling from service API. So the way this works is you have service web that calls service API that calls service hello, basically. Again, same thing. I'm saying make it available in 1991. I don't care where it is. And I'm responding with some text. I'm just saying I'm service API running on Kubernetes. Then you have service hello, same thing here. But here I'm not providing any upstream. So this is where our service path ends. And I'm just returning hello world. That's it. I have no upstreams, basically. So I'm not calling anything. All right, so I'll apply this. So I'll do kubectl apply, and I will do services, I think. And most of these services are here. All right, so I think I had already created them, and you should be able to see them in the here. So if I see service API, I ignore these health checks because I'm running a version that has some, it's a dev build. So I'm testing with some things here, but you kind of get the idea here. So if you see web, this is the topology view that I talked about. You can actually see, let me make this bigger. You actually see service web is dependent on service API is dependent on service hello, and service hello, that's it. It doesn't depend on anything. That's kind of the idea here. So what I've done here is that I've actually created a service. So if you see, if I switch back to service web, I've actually created a really simple Kubernetes service, which is just a load balancer that points to service web, which is our entry point, basically. So we have, if I do kubectl get service, I should see a load balancer. This is, yeah, there we go. So this is the public IP of the load balancer. So I can just do curl HTTP that. And hopefully, okay. So far the demo hasn't broken, which is very impressive. Believe me, because this wasn't working before this. So yeah. So service API is able to talk to service thing. And then I think this is better visualized because I think this one has a UI. So if I go here, oops, let me open this. Cool. Yeah. So if I go /UI, I think it's much better to look at. Yeah, there we go. So you see we have like service web talking to service API and then service hello. Fairly straightforward, nothing crazy here. What we could do is we could try to break this and we could actually create an intention. So if I go to services, and this may or may not work, by the way. So I'll try this. So this is what I was talking about initially, which is that authorization. Is service API and service web, should they be talking to each other, right? That's kind of the question. So here what I'll do is I'll say all services from all services to service, let's say service web is talking to API, or maybe let's do service API. Actually, let's do service hello. Yeah, let's do API. I think it's better to try API. So this should basically stop all the requests coming in. I don't know if these services were enabled as HTTP, but let's try this TCP block basically. And we'll hit save. And then if we try this, okay, so I think there we go. So you'll see immediately, there's a bad response, 403, which is like unauthorized, which is what you kind of see. So how did this work, right? So the idea here is that authorization call actually is done via, the authorization is implemented via Envoy. So if I actually look at, so if I do kubectl get pods, and if I grep for, let's say, oops, sorry, it's like 9 p.m. here, so I apologize if I'm mistyping here. So if I do kubectl describe pods, so you'll notice there is, first of all, let's do get pods actually. That'll give you a better idea. Get pods. So you'll notice there's 3 containers, but I just defined only one here, right? There's like actually 3 that is, there are 2 more containers that were injected for me. And that happened by, that happened using a webhook that console automatically does that for you. But it did inject, I'll show you the Envoy proxy, I think, right here. So you'll see this is the console connect Envoy sidecar. This is the Envoy proxy that's running alongside this application. This is the one that implements this authorization. Now the control plane is console. It's this console server that is basically created using the console servers. And this is the one, this is the piece that needs to be highly available for you. So here, if I delete this, hopefully this works. Let's go back here and I see service, I think it was service web. Yeah, service web. Yeah, so you see that they're still healthy. They still can talk to each other. If I refresh, hopefully everything just works. So yeah, so far the demo hasn't broken. This is great. This is beyond my expectation already. I can end the call at this point. I can just not take questions. I'm just kidding. We'll keep going forward. We'll do a few more demos until we break something, right? That's the idea here. You all anyway want me to fail, right? That's the whole point of a person doing live demos here. So let's try that out. So okay, so that was the basic like authorization bit that I really talked about in a proxy. And this is done at like L4 level and also L2. So I could create an intention. Let's say if that was an HTTP service, I could create an intention which is application aware. So you can create a permission. I can say, hey, like, deny everything that's going to a path that's prefixed by, I don't know, hello or something like that. So it could be as complex as that. And only the requests that are going to /hello will be the ones that are getting those 403s. The rest will just work. And these are the L7, in which you actually inspect the packet, right? And this is the difference between those, like the L4 versus L7, rules. There is an overhead to this, right? Like, in reality, all mesh vendors will never talk about this. But when you think about this, like in practicality, you're reading every HTTP request, you're actually inspecting it, seeing what the path is, and so on, and enforcing it in that way. So you can do that if you like, basically. All right, so that was your intentions demo, right? So next thing, and you'll notice I'm also running this mesh gateway, and I'll talk about how that all comes into play here. So next thing I want to show is maybe a failover to another data center. So I'm hiding a few details here, and I'll talk about these details in this grand reveal later. So I have these two data centers that are already linked to each other. So you have DC2, as you can see, and DC1. So these are two console data centers. They're running their own independent servers. They have their own independent state, but they are aware of each other. So I can do things like, I can do things like I can do members, I think. um, and this will kind of tell you what are the members of this, of the cluster. But also, if you see, I'm putting a van flag, which kind of tells you, hey, like, give me all the members in, that are connected to each other, like all the data centers that are connected to each other. So you see all these servers, some of them are DC1, some of them are DC2, are actually seeing each other, and they recognize each other. So what can happen here is that a service running here, a service, maybe service web or service API or service hello, can request a service in another DC, and it should just work using the mesh gateways. So the mesh gateways, actually, there's mesh gateways running here, there's mesh gateways running here. All these two mesh gateways, they actually are allowed to talk to each other. These are publicly accessible. But as I said, they have like enforcement of security. They have the SNI kind of based routing available. So you can actually use that to do something. So let's do something interesting. So what I'll do is, as you can see with this app, we have service web. Oops, that's not good. Okay, as I told you, there could be some errors here. Okay, I hope this all works. Okay, it's working. So service web talking to service API, talking to service hello. What I'll do is I'll create service API in another data center, and then route all the traffic from service web to service API in another data center, and then maybe use the service hello in that data center. So basically, only service web will be in DC1, service API will be in DC2, service hello will be in DC2 as well. That's kind of the idea here. So here I have another Kubernetes cluster, which is running here. So what I'll do is go to DC2. I'll show you these applications. They're nothing special here. So if I go to, what is this, service to redirect, is it? Yeah. So let's say service API, right? So this is basically the same service API. There's nothing that says this is running in DC2 or anything like that. I'm just saying this is service API, same response. There's no trickery here. Same thing with service hello. I'm not saying anything. It's not different than any other service that you saw already. So okay, so I'll do, let me just quickly check in this cluster what's running. I don't remember if there's anything running here. All right, so there's nothing running except all the console stuff that you already saw from the previous cluster. So what I'll do is I'll do kubectl. Actually, I can do kubectl apply. I can do service. I think it's redirect. Yeah, and then that should redirect. And I'll create these services, do get pods, and maybe just grep for service. All right, so we are initializing these pods. Again, you'll notice instead of one container, there's three, which is the sidecar proxy that's coming online. And now these are running. So now if I go back to maybe DC2, all right, so this one, ignore this health check that's failing. This is because I was just trying something and I pushed it to the limit here. So ignore this one. This is the one that's meaningful here because this is just one instance running. So you see, if I go to service API, it'll say it talks to service hello, and then service hello basically it doesn't talk to anything. It's the same topology, but only the second half of that basically. All right, so that's in DC2, right? Now what happens is, so what I did is actually lied to you that I didn't really say where this DC2 was. I think some of you probably got this, but this one's running in DigitalOcean. The first cluster was running in Google in US East. This is running in DigitalOcean. So we are being even more ambitious with this demo. So if this fails, there's you can't blame me because this is not doable. It's impossible that this works, right? So we'll see how this works. All right, so what I'll do is I'll actually define something called a service redirect. So I can show you what the redirect is. Open this and this, okay. So I'll create some service defaults for service API. So I'll say, hey, this service is an HTTP service, and I will tell it that, hey, use your local mesh gateway if there is any request that requires to go to service API. Then I'll create a service redirect. I'll make this bigger. Which says, resolve for service API, resolve it, but actually redirect it to DC2. Do not use your local DC service. So DC1's service API would not be included here. All right, so what I'll do here is, now this is where it gets very exciting. We go kubectl, go console. I'm on a console server here, but you can do this using the API or other ways you using Terraform or something like that. But you can, here I'm just keeping it very simple. So I'm gonna just maybe quickly view the service default for service API, just make sure it's all good. Yep, looks good to me. So I'll do console, oops, console, I think it's config, right? And I'll say service API, and I'll create the service default. Just say that, hey, like it's an HTTP service. It should be, it should have the mesh locally available to it. And then I'll write service API, and I'll create that redirect. I think, where is it? Service API redirect. Okay, so before I create that, I want to show you how quickly this actually works. Now, if I fail here, like it'll be unfortunate. This is gonna be super embarrassing for me, but it's okay. I'm okay to do this. This is a very friendly group, so I don't care really if this fails. So let's see. Oops. Yeah, I can just do this, and we'll just watch it every second. And you currently see, okay, what you want to notice here. Oh man, this is going off the screen. Let me, oops. Okay, how do I, maybe I can just, okay, give me a second. Let me move this here and make this a bigger a little bit. All right, so what you want to watch is this service API call, right? This service hello, service API. This should say, running on DigitalOcean. This should say running on DigitalOcean, if this works. And this might not work, but we'll see. All right, so is everyone ready for this demo? So I'm going to hit enter on this right of the screen, and you'll all watch me fail. I don't know how many people have joined. Let me check. There's 43 people, so no issues here. So okay, there we go. So if I do this redirect, you immediately see that now it says DigitalOcean, DigitalOcean. This is, I guess I didn't fail, but in reality, I should have really failed at this point. But yeah, as you can see, the redirect happened like quite quickly here. This happens in matter of like, it's under a 1.2 seconds right now. We are doing a benchmarking to kind of figure out like how quickly does the endpoint propagation and service resolutions actually work. And we'll publish that benchmark. We'll also publish an open source how we do that benchmark. But that's kind of the idea here. I could actually change this. Now, this is, again, pushing the limits here. I have not tried this before. So let's see, let's do the redirect. Let's actually just delete the redirect. I think that should mess things up for sure. So let's do console config delete. I can say kind. I can say, I think it's a service resolver. And the name should be just service API. And this should delete that resolution rule that says, hey, redirect it to DC2, and it should just default to whatever it was doing, which was local. This might not work again, but we'll try this. So just watch this and this here. This should just say Kubernetes as soon as I hit enter here. So I'll do that. And immediately you see, without dropping any traffic, we see there's a service API running on Kubernetes and thing. And the reason why this works perfectly is because console is keeping, health, it does health checking too, right? So if I go back here, I open service API, if I see instances and see this, there's multiple health checks that are running on the service. You actually didn't define any health checks, means you probably saw my definition here. I actually didn't define any health checks anywhere except for the just basic Kubernetes liveliness probe. So what happens is, Connect is intelligent enough to read this config and say, hey, you have a liveliness probe. I'll actually just register a health check for you. And as soon as this fails, I'll actually mark this service to be unhealthy, and it shouldn't work, basically. So that's kind of by the way, all of this communication actually happens over the mesh gateways, which is what I was talking about. And these are the two things that you need to kind of make sure that they talk to each other. You can't reach that service from DigitalOcean's IP address to like this thing. I'm not creating any VPN. I'm not doing anything. This is all on the public internet, but it's all encrypted via those mesh gateways using Console Connect. So I think those were most of my things. Let me switch back to the slides here. So yeah, I guess this in summary, like console is like a fully featured, like mesh does a bunch of stuff, multi-cloud as I showed you, multi-region, which is, the DigitalOcean. I think if I switch to, I don't quite remember, but yeah, this one's running in Canada, actually, Toronto one. And I don't know if you can see that. You can also see my last month's usage, very low because I hardly use DigitalOcean here. So this one's default Toronto one, I think. I think that that other cluster is running in GKE, and this is running in US East, basically US East B. So I wasn't really faking it, and if I delete this, it'll probably take everything down. So just to clarify. All right, so let me switch back to the slides and oops, and switch here. All right. Oh yeah, that's it. I will be uploading my slides to this link. Right now, this link wouldn't work, but maybe after the talk, I'll just export everything to PDF, and you should have this in Speaker Deck or something. So it's just mishra.dev/service mesh distributed meetup systems meetup. I can copy this link and give it to Nishant, and maybe Nishant, you can
Yep,
send
I'll
it
do
over.
that.
So I think that's it. And so this was a talk on console and service mesh, and kind of give you in context of where it all started, and some real life implementation. As HashiCorp does create many different projects. If you have any questions about like other HashiCorp projects, I can try to answer them to my best of the ability. It is 8 projects now for us, so it is quite crazy at this point. It's hard to keep up for me. Even I work at the company. But I'm happy to answer any questions if you do have questions.
Hey, Anubhav, nice talk. And the question is, you've used a load balancer. Is it layer 4 load balancer or layer 7 load balancer on GKE?
Yeah, so that's a good question. So the load balancer, it's actually I think in GK currently I think it's just an application load balancer. I'm not sharing my screen anymore. Sorry, it's just an application load balancer. It's a layer 7 application aware load balancer. But in by default, most cloud providers will just give you a TCP load balancer. Like in Amazon, if you create a Kubernetes service, it just gives you an ELB that's using the classic ELB, which is not the ALB and not the NLB. There are other like ingress controllers that you can use to put in traffic. Console actually has an ingress primitive as well, like how you saw the mesh gateway primitive. There's also an ingress primitive, but you still need to front it with something physical, like not physical, I guess it's virtual, but like something that actually is publicly accessible. So you might need to make the VM that's running that ingress gateway public, or you might be, if you're using it in Kubernetes, you might need to front that ingress controller with the ingress primitive with an ELB or something like that, or Google's cloud load balancer.
So the answer is it is a application load balancer, and it is layer 4, correct?
This is layer 7 actually.
Layer 7. So if it is layer 7, then in your services, you have mentioned the path-based routing, correct?
Mm-hmm.
And you were saying you used a layer 4 console as the API service you mentioned.
Mm-hmm.
Is that right? So how does it gel? On the outside, it's a layer 7, and in the inside, in your services, it's layer 4.
Yeah, so basically, what's happening here is like the traffic is coming on HTTP. I think Google has I don't actually quite know like the Google load balancer primitive, so apologies on that. But I think Google has these ideas of a front end, and then you have these back end streams. So what you can do is you can actually connect an HTTP request, and then point to a TCP port that it should go to, and then maybe a path or something like that. So, but I don't know what the default the default is for a Kubernetes load balancer or something like that. So let's take a more easier example. So in Amazon, you'll just get a TCP load balancer. That'll just basically, if you're running on 80 port 80, it'll forward it to the pods that are running on a certain particular port. So when you expose a pod in a service, so if I show you here, I think it's in service web. Yeah, so here if it says like this is TCP, this should actually I might be wrong. This should be a TCP.
We can't see your console, yeah.
Oops, sorry. 1 second. Let me quickly share. I think it's this one. Yeah, so I think this should be a I don't think this is an application load balancer. This is a layer 4 load balancer. Yeah,
exactly.
So I think,
yeah, it's a layer 4. Yeah, it's a layer 4. So coming to that, if you see slightly above of one of your services, so this is a layer 4, right? But if you see your service YAML, right, service YAML definition, you have path-based routing there, like
No.
a slash hello, you said, right?
No, we don't have any path-based routing. Actually, I'm not defining any path-based routing rules. It's very simple, actually. The request is coming in on port 9090, and then the web server that's listening on that route just returns results.
No, where is your service YAML definition? Service hello YAML definition? Can you go to the service hello? Service hello dot YAML. Yeah. So here, see, the path is slash health. Oh, no, forget about this. Where is the other one? Okay, so you don't have yeah, this is the one I'm talking about. But when you hit the endpoint, right, you had an IP slash hello, correct? Or something like that when we were checking?
No, I don't think I'm using any path-based routing, actually. I'm just using like very simple services. In this case, this health endpoint is just the liveliness scope for Kubernetes. And then there's no path-based routing, basically.
Okay. Assuming if I want to have a path-based routing inside my, let's say, service hello.yaml, right? So there'll be two, let's assume there'll be two paths, slash hello 1, slash hello 2. So in that case, my layer 4 load balancer will still work. How is it? Because I tried it many times and it worked for me. I was just curious.
Have you tried console?
No. I mean, just the GKE and Nginx ingress controller.
Oh yeah, so I have no idea how the Nginx controller does that, but yeah, it means in our case, I think it's what I explained you. I think explained in the talk here. So if I share my talk, it's like quite straightforward. I think I might have gone there too quickly.
Or just to put it this way, in your case, if I put a path-based routing in the services, it will fail because we are using layer 4. Are you saying that?
I actually haven't tried that, but I can try that for you at some point. Maybe we have some time at the end. I can try that. I actually can't answer that.
Oh,
I'm not quite sure what happens. Yeah.
Fine.
It shouldn't. I don't think it should fail, but
yeah,
we can confirm that
the service still goes through. The service still goes through. So that is where I was a bit confused. Like, how will you actually choose between a layer 7 load balancer and a layer 4 load balancer? Was my final.
I think by default, like if you're using Kubernetes, means as far as I remember, like I don't work with Kubernetes every day. It might have changed over time, but maybe someone else on the call can answer that. But by default, when you create a service and you expose it, you get a TCP like load balancer on most clouds. If you're using ingress primitive in Kubernetes, then you can actually do more things. Like you can actually front it with like an application load balancer. Or you can do other like intelligent routing related things. But I think by default, you should just get a layer 4 stuff.
Okay, great. Thank you.
Yeah, no problem.
I think we have 5 more minutes. So if there are questions, let's go for them. I think it's quite late for Anubhav otherwise in the day.
Oh, I see my friend Tardik. Hey Tardik, what's going on, man? Sorry about that.
How are you doing?
I'm good. Any other questions?
Hey Anubhav, thanks for showing us the magic. So like
magic.
So do you see like the plugins or the traffic shaping as a first-class citizens in Kubernetes, like? Or we will keep on using the plugins like console or for that matter, Istio and all.
Oh yeah, that's actually a good point. So I think means, okay, so I have to just, this is not HashiCorp's opinion. This is like my own opinion. So I've been working with Kubernetes since when I was when I was in my operations engineering role, since pretty much when it was released. So at that point, we were using Mesos as a scheduler, and then we moved to Kubernetes. And there were decisions that we made to why we moved and so on. But when we did, what we did like is that service primitive, right? Where you had which I showed you, which is like, hey, you just say like what port the service should be available. You get a load balancer to front it, but that's it. You don't get anything more. I think what was promised early on, I think, was that you would have this, you would have a new primitive. That primitive would probably be an ingress controller or something like that, and it would do things like multiple service routing. Because if you have, like, let's say in Monzo's case, 1,500 services, and let's say at least 100 of them have to be exposed to the public or something, and needs to be public services, then you realize like how many load balancers you have to spin up. Each service becomes its own, has its own load balancer. It's like impossible to do. So you really need like something to do this for you and multiplex things along. So what I thought was that ingress primitive in Kubernetes will be the one that does that. But I think that people solve this problem multiple ways. So you have you have this idea of like the east-west traffic, which is what Console Connect's kind of allowing you to do, is like do east-west stuff, but not south traffic. That stuff has to come through using a ingress controller. Using using an ingress, something called an ingress, like as a concept. So that's why we have, I think, something called ingress, which allows you to do the north-south traffic. But this concept actually doesn't scale for every Kubernetes, for every environment, for every for every deployment of your application. It might be a VM, might be bare metal, might be. So to give some form of consistency, that's why you have tools like Console to kind of do that for you consistently, regardless of the environment. But in Kubernetes itself, this, I really hope that at some point, this is my own personal opinion, application developers get like first class, like something that's built into Kubernetes that does all of this stuff for you. So by default, the services, the pods are allowed to talk to each other. That's not good for security. So you really need some form of network policies. Kubernetes does have network policies and stuff. But then again, maybe you can use something like Calico, which is an overlay network. But then again, you're adding complexity of running BGP in your data centers and stuff like that. Ideally not the best, right? You're already running in a very hyper virtualized environment. Then you run another set of stuff, and then another. And this is just turtles, right? At some point, where is this application going to run, right? It's very difficult to relate to. So I think the solution should be that Kubernetes should do this natively. But in our opinion, what we've seen, especially with the customers, like the names that I talked about, Twitch and GitHub, no one is pure one environment. Like your data center is usually at a large scale, because you acquire a bunch of companies, it is going to be a heterogeneous environment. So it is going to be, a mix of Kubernetes, mix of VMs, mix of bare metal, mix of, containers, serverless. Like there's going to be a lot of stuff that's going to be running alongside, and everyone wants everything to talk to each other. In most cases, they want some form of consistency to do service discovery and stuff, and hence solutions like Console or maybe Istio. Istio, I think currently only works on Kubernetes and maybe some VM stuff. But so you need solutions like that to consistently do that for you. But ideally, means I'm a big fan of the platform should do everything for you, and you don't need to install anything extra, and then keep it very simple. Once I learn the platform, I should know about everything. I shouldn't be learning 7 other tools to get my job done, basically.
Correct. Yep. Thank you, Anubhav.
No problem.
Anubhav, can you show us the configuration for the mesh gateway? I just was curious how the DC1 talks to DC2. What was the configuration there?
Oh yeah. Okay. So, all right. So I can share my screen quickly. I think I can just share this, and then, okay. So so this was installed using a Helm chart. So I can just do kubectl get pods. I'll just grab you I misspelled this. Okay, I'll grab you this gateway, and let me close this. So it becomes, I can do full screen here. Okay, so let's do kubectl describe pod, and I'll show you what gateway is running. So, okay, so gateway here, all we do really is in gateway, we configure it using an init container. So you see this is a service init container. So it basically runs this tool called console K8s, which ships alongside console. So this is not built into console. It's like a separate binary. Eventually, this will be part of console as well. So here we define a few things, like, for example, we do, oops, someone's mic. You eventually define things like the Kubernetes gateway, and then you say like, this is just a mesh gateway. Oops. Oops. I don't know who's speaking here. Okay, so I'll continue. So you need to define and then all you define is like the address, the WAN address that it's running on, and this address is basically a public Kubernetes service. So if I do, I think it's get service. So this is just a load balancer IP here, right? And this we basically bind on, and we don't care which gateway we basically route the request to, because both gateways have the information that you really need. So if I scroll up again, so yeah, that's the gateway address. It picks that WAN address, and that's all you need. So now the magic happens when you do when you WAN join two console data centers. For example, you join the servers together. The gateways, the gateways actually now using, we also, as I said, I skipped a lot of like architecture stuff. I apologize for that. But we run a gossip layer, which is a gossip protocol that we run in console. So basically every node knows about every other node. And this is done using, you can read up on it. I'm not going to extend this talk even longer. But the idea here is that gossip network also has a WAN pool, which is basically made up of only the servers in this case, right? So the servers know about each other using this WAN gossip pool. And once they share information, they also share information about, like, there is a gateway service. If you notice in our web UI, we have this mesh gateway also registered as a service. So this is something that console actually sends across between every data center and says, hey, we have all these mesh gateway, and remember, there are exceptions. These are the ones that are exposed to the internet. And then you make sure that the firewall rules just allow the gateways to talk to each other. That is something that console cannot do. You have to do that and configure that, but that's the only thing you really need to do manually. And that's it. And then you define that, and then you basically give it some config, like what port to run on, some LAN addresses, WAN addresses. LAN is for just locally accessing stuff for pods, and then WAN addresses is that, the load balancer IP that I saw. And so the mesh gateways in DigitalOcean and Google, they just dock on that WAN address. And then once they do that, then they basically convert the call into a local. So they kind of do what we do with NAT gating and stuff like that. But they do that using like, using like SNI headers and so on. So that's kind of long form. I don't want to extend this longer, but yeah, that's kind of the long form answer to your question.
Thank you so much.
No problem. Cool. All right.
All right.